Hey everyone, and welcome to our second lesson in our unit on matter and energy. Today we're going to take a look at a couple different types of energy, namely potential energy and kinetic energy. And we will work on some skills practicing converting between the Kelvin and Celsius temperature scale. And that's going to be our main goal for today, is to be able to take temperatures and convert between those two temperature scales. Now on the first slide here we have a transformation of potential energy into kinetic energy, as these scissors cut this string attached to this weight that then falls down to that what looks like a big wood spike in the ground. Stored energy due to this weight's position above the ground gets converted into kinetic energy, which we should know as energy of motion, and it can then transfer its force down onto that wooden peg. And we have similar transfers of energy in the field of chemistry, but we generally see those not necessarily in the motion of macro objects, but in the motion of atomic objects moving around. So energy is defined as the ability to do work, which really is using some type of force to move an object some amount of distance. And the two types of energy that we're going to focus on are kinetic and potential energy. Kinetic being the energy of motion, and potential being stored energy, usually due to position above the surface of the Earth due to gravity, or due to stored chemical potential energy. Now, as we said, kinetic energy is the energy of motion, and it's contained by anything that moves, whether it's on the macro scale or the micro scale. Now, as far as some Regents prep goes, you're going to see a pretty common question when we do some practice, and the Regents likes to use this phrase, average kinetic energy, and it makes sense, but really you can just take that and cross it out and replace it with the word temperature. Reread the question and then answer it. Now, atoms and molecules are in motion. They're always in motion. And they will move faster when their temperature is increased, because temperature, again, is referring to average kinetic energy. So when we're taking the temperature of an object, what we're really doing is measuring the average kinetic energy of every particle in that sample. And we relate that to the temperature of the substance. And we would use a thermometer to measure temperature. We see that there. If we replace average kinetic energy with temperature, what tool would you use to measure temperature? Well, that's a thermometer. So we really use two different temperature scales in this course. You guys are probably more familiar with the Celsius scale, which is devised by Anders Celsius around 1742. And the way he determined the scale was by the melting and boiling point of water. What he did was, with a sample of, I believe it was mercury in a hollow tube, he put that tube into liquid water, and when it froze, wherever that line was, he marked a 0 point. And then whenever it was boiling on that tube, he marked boiling point, which would have been 100 degrees Celsius. So whenever water froze, he called that 0, and whenever it boiled, he called that 100. And that's kind of how we get the basis of the Celsius scale. And we see the Celsius scale beneath here in green. And then we have another scale above it in K, which is our Kelvin scale. And these two are related to each other. So the Kelvin scale was devised by Lord William Thomson Kelvin, and it uses the Celsius size degree, meaning if we change 1 degree Celsius, we also change 1 degree Kelvin. But the Kelvin scale was reset so that it starts at 0 Kelvin, and that's the lowest temperature on the Kelvin scale. Celsius, we can go into negative numbers. We can go down to minus 273 Celsius. There is no negative on the Kelvin scale. At 0 Kelvin, which is also minus 273 Celsius, this is when all particle motion stops. So any atom or molecule that would normally be moving have some kind of kinetic energy. When it reaches 0 Kelvin, this is what we call absolute zero. And it's the point at which all matter stops moving, at least the matter that's has its temperature of 0 Kelvin. This has been approached in a lab, I believe down to a thousandth or 10,000ths of a decimal, but has never actually been achieved completely where the molecule stops moving. Theoretically, it would happen, but it has not been able to be obtained in a lab yet. So really the goal here is to be able to convert between different temperature scales. So the melting point of water we know is 0 Celsius, and that's going to be equal to 273 Kelvin. And this is our key for converting, is the number 273. Now on the back of your reference table, we have an equation that indicates how to convert between the Kelvin and the Celsius scale. And depending which temperature we have, we plug it into the value in the equation and solve for the other one. When we have a temperature of 0 Celsius, we plug that into our part of the equation here, add 273, and we get 273 Kelvin. So those would be equal temperatures. The boiling point of water we know is 100 degrees Celsius. So we add 273, just like we see in our equation here. So the boiling point on the Kelvin scale of water is 373 Kelvin. Now remember, when we're talking about temperature change, a 1 degree change on the Kelvin scale is equal to a 1 degree change on the Celsius scale. To convert between the two, we're either going to add 273 or subtract 273. Now for this first example, we want to convert 42 Celsius into Kelvin. So we're going to use our equation. K equals degrees Celsius plus 273. We'll plug in our 42 degrees Celsius and add 273. And we're going to get a Kelvin temperature of 315 K. So that would be an equal temperature to 42 degrees Celsius. Now converting 313 Kelvin into Celsius, I'm going to keep the equation written the same way. You guys can feel free to stop the video here and try these and then check your work. We want to convert 313 Kelvin into a temperature of degrees Celsius. Solving for that degrees Celsius, we'll move over our 273. And our temperature in degrees Celsius comes out to 40 degrees Celsius. Potential energy is stored energy. It doesn't have the ability to do work right now, but if we release it, then it will have the ability to do work. We find potential energy in coiled springs, on a car, on a slinky, other springs in general as well. Chemical bonds contain a lot of the energy that you would release in food. Objects at a height above the surface of the earth due to gravity. And I guess this food's going to contain potential in its chemical bonds, but chemical bonds are also going to contain energy in any molecular compound, not just in food. So even in water, the bonds between hydrogen and oxygen contain chemical energy as well that can be released when we break those bonds. Now, since stored energy cannot be measured directly, we can't take a device to my sandwich I had for lunch and measure how much energy is in there. You can't put it on a scale and measure that. We have to then convert that potential energy into kinetic energy, and then we can measure how much energy was released. And to do this, we're going to use a device called a calorimeter. And the calorimeter is going to measure energy stored in a substance using the unit joule, which is a metric unit that measures energy. In this case, we'll use it to measure potential energy. Now 1,000 joules is considered a kilojoule, and that's what we're going to use to measure potential energy changes in either physical or chemical reactions and changes. And we'll have to make sure that we know how to convert between those. Now, since joule does not have a prefix in front of it, this is going to be a base unit, and therefore its factor is times 10 to the 0, and a kilojoule with a prefix kilo has a factor of times 10 to the third. So this means we're going to have to move our decimal 3 spots to the left or to the right, depending on which direction we are converting. Now, if we go from a smaller unit to a bigger unit, we're going to move the decimal 3 spots to the left. If we go from a larger unit to a smaller unit, we're going to move 3 spots to the right in order to make the number bigger. So let's try a couple examples. Feel free to pause these and try them, and then check your work. And I'll do these in a couple different ways. So we're going from a kilojoule to a joule. So we're going from a larger unit to a smaller unit, which means we're going to want to move this 3 spots to the right. So this becomes 2,588 joules. How many joules are there in 22.33 kilojoules? Well, in 22.33 kilojoules, if we have 1,000 joules for every 1 kilojoule, it's our conversion factor, and we multiply and our kilojoules cancel, what we end up with is 22,300 joules. And again, that's just moving the decimal 3 spots to the right. Now, going from a larger unit to a smaller unit, we're going to move the decimal the other direction. So going from a kilojoule to a joule, we're going to go 3 spots to the left. So this becomes 2.3564. Remember, when we're converting, we're using the same number of sig figs in the number that we're converting and making sure we keep all of those, in this case 5, in our answer. And this would be kilojoules. And again, I'll show you using dimensional analysis, 12.3 joules times 1 kilojoule in every 1,000 joules. And we'll multiply, joules will cancel, and it becomes 12.3 divided by 1,000, which means this becomes 0.0123 kilojoules. 3 sig figs in that answer, just like we have 3 sig figs in our original number. Now we will do a lab using a calorimeter and using calorimetry, which I'm going to explain here. And this is a real simple calorimeter cup. And what this device does is allows us to measure energy changes happening in some type of reaction. And that reaction may either release energy when it occurs, or it might absorb or take in energy in order to occur. We have a stirrer here that's going to move up and down, and that's going to allow the mixture to stay evenly mixed and allow the temperature to remain as even as we possibly can. We have an insulated stopper here, which is going to prevent any of the energy inside from being lost to the surroundings. We want to try and keep this as a closed environment so we're not gaining or losing any energy from the outside. All the energy that occurs in this reaction, we want all of that to be absorbed by the water that is contained around the reaction mixture. And I'll explain what that water is going to do in a minute. So heat flow, if we think about this in the calorimeter, heat's always going to flow from where it's hot to where it's not, which means whichever the warmer or hotter object is, it's always going to transfer heat to something that is not as hot. It doesn't matter if it's a big difference or a small difference. Whichever one's warmer, it's going to transfer heat to that cooler object until they reach an equilibrium point, or until both those objects are the same temperature. Kind of like if you put your hand down onto a table and you leave it there, your hand's going to continue to transfer heat into the table until that table is the same temperature as your hand. Now for exothermic changes, measuring exothermic changes in a calorimeter. we might have potential energy that's stored in some substance that gets released. And in order to measure it, we need to convert it into kinetic energy. And this change of heat, when it's being released, change in heat being delta H, change in H or change in heat, is going to be negative. So a negative change in heat means that energy is being released. And that's what we call an exothermic change. Exo meaning that energy is exiting or leaving the reaction or the environment. And exothermic reactions are going to feel warm because they're giving off energy, they're giving off heat. Think of a fireplace or a fire burning wood. That's chemical change. We're not left with the wood at the end of the fire. It's very warm. We see light that's coming off. It's energy that's being released and given off because of the reaction. Now, if we perform an exothermic change in a calorimeter, say by burning wood, or having some type of reaction that's going to release heat, the kinetic energy that's given off by the reaction gets absorbed by the water in the calorimeter cup that's surrounding the reaction. So that water, the molecules of water, gain the kinetic energy from the reaction that was released from the potential energy of the reaction, and this causes the temperature of the water to increase, meaning the average kinetic energy of the water molecules are going to increase. So that potential energy from the reaction gets released to the environment. It gets absorbed by the water molecules, which causes their kinetic energy to increase. And using this property called specific heat, we can actually measure how much energy is being released or absorbed. And that's because we know the rate at which water absorbs and releases heat. And it does so at a rate of 4.18 joules, or it's going to take 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. So if we know how much water we start with, and we know how much the temperature changes of the water, we can determine how much energy was released by the reaction. And this is done very commonly when measuring the calorie content in food. So we would actually take a peanut, burn it in a calorimeter or similar device, and we measure the change in the temperature of the water. And depending how much that changes, we can use a simple equation to determine how much energy was released from the peanut. And once we have that number, we call that a calorie. Very similar to a calorimeter. Calories are another measure of heat. So they're very similar to a joule. So when we burn the peanut, the energy contained in the peanut gets converted to kinetic energy. Molecules start moving faster. Water molecules start moving faster, and the temperature of the water is going to increase. I'm going to show you a quick little example of this, and we'll see how smoothly this goes. So I have a little setup here, and what I'm going to do, let's see, we have our temperature going here. We've been recording temperature since the start of our presentation. And what we have is a temperature about 22.3 degrees Celsius. Now, I measured this amount of water with a graduated cylinder, and there's 150 mils of water in there. And the density of water is 1 gram per milliliter, so 150 mils of water is going to be 150 grams. And we use graduated cylinders to measure volumes of liquids because it does so accurately. The measurements on the side of the beaker they're indicators, but they're not very accurate. So I have a temperature probe in here, and we're monitoring the temperature of the water inside. We know the mass of it. So if we were to have some type of reaction that occurs in here, depending on how the temperature of the water changes, whether it goes up or down, we can determine how much energy was given to it or even taken from it. Now, to give you an idea, hopefully this is all working correctly, I have a little flame going here. And what I'm going to do is take this little brass weight and put it into some heat. This might be a little hard to see. Okay? I'm going to get this a little hot. Nothing too crazy. We don't need to do anything. I don't need to get it glowing red or smoking hot or anything like that. What I want you to see here, I'm adding heat to this. I don't know what its temperature is. I don't know how much energy I'm adding to it, but I'll explain this in a second. If we consider this like a reaction, when I put this into, looks like that might have restarted. If I put this into our calorimeter here and drop that down, what we see is a pretty big temperature spike. And on this temperature spike, if we can determine the difference here in this temperature from high to low, and that's from 22.5 to about 24, that's a change in 2 degrees Celsius. Given 150 grams of water, we can determine exactly how much energy that was given to the water. And whatever was given to the water was lost, we assume, by, in this case, the metal weight, or the reaction, or the food, or whatever it is that we're burning to try and determine how much energy was contained. We could then take that amount of energy, and assuming that the energy gained by the water was lost by the metal, we could then use our calorimetry equation, which we'll learn next lesson, and determine exactly what the final temperature was of that metal. Now, an endothermic change is going to be the opposite of an exothermic change. And since exothermic reactions feel hot, endothermic reactions are going to feel cold, because endothermic changes are going to absorb or take energy from the surrounding, and they're going to convert that kinetic energy of air molecules, of the bench, of anything that is around the reaction. It's going to take energy from there, and it's going to store it into the bonds of whatever the reaction is doing, creating or changing. And this is going to cause the temperature of the water or the surroundings to decrease. And this means that we're going to have a change in heat, a delta H, as a positive value. So when we see delta H, or changes in heat, as positive values, that's going to tell us that the reaction is endothermic, and it's going to take energy from the surroundings. Now, the law of conservation of energy, I kind of made a brief mention to this a few moments ago. It says that energy can't be created or destroyed by chemical change. It's only converted from one form of energy to another. Now, the energy that I put into that brass weight, I assume that when I put it in the water, it all gets transferred into the water, but as I'm transferring it, some of it's being transferred into the tongs, some's being transferred to the air, some might be transferred to the thermometer that's in the calorimeter, in this case in the beaker. But it's going somewhere. It's not being created or destroyed. It's simply being converted from one form into another. And a key here is that this is true for chemical change. When we talk about nuclear change later in the year, this is not necessarily the case. So if we consider a reaction A plus B yields C, this arrow meaning yields or produces, if we know that our reactants A and B have a total of 80 kilojoules, this is energy that's stored in their bonds, and the product C contains 20 kilojoules of energy. Well, this doesn't quite make sense, right? Because 20 plus 60, if we start with 80, we end up with 20. We're missing 60 there. And that's the 60 represented here, okay? And we have to show that as energy being lost. We started with 80. We only showed 20 in the bonds of C. So where did that 60 go? Well, it's not created or destroyed, so it has to go somewhere. It's going to be released or lost in the reaction. So we represent that by showing we have 60 kilojoules of heat being released. And now we have 80 kilojoules on both sides of our arrow. We kind of treat this like an equal sign. And since we have 80 and 80, these now satisfy the law of conservation of matter. Now, if we were to carry out this reaction in a calorimeter, the temperature of the water inside the calorimeter is going to increase as that newly formed and released kinetic energy in the form of heat makes those water molecules move faster. We will cover calorimetry more in our next lesson. If you guys have any questions on any of this, make sure you see me and get your questions answered. Hope you guys have a great day.